And cool. Okay, so let's review a little bit what we were talking about last time, and we'll take it slow again, but I'm gonna try to finish today so we can be done. By the way, any volunteers for next week? I think there's only a couple students here, but maybe someone wants to talk. Well, anyways,
we can discuss later.
Yeah. So maybe Alice will show up and we'll pressure her. So let's recall what we were doing last time. We were talking about this Riemann-Schottky problem. What does it say? Well, we started with motivation. We talked about the Riemann mapping theorem, how it holds for simply connected domains, which are not all of C. Important point there. And well, if you have doubly connected domain or any domain with more holes, well, two domains aren't necessarily conformally equivalent anymore. But there's a number of parameters you can determine called the moduli of the domain, which tell you whether or not, well, two domains will be equivalent or not. So the Riemann-Schottky problem is, well, related to those parameters. It asks, so well, before we talk about what it asks, let's go back and look at the one for Riemann surfaces. That's what I want to talk about. So for a given Riemann surface, with a fixed homology basis, a fixed basis of cycles, appropriately normalized, and I wrote the normalization somewhere here, we can define a mapping into what's called the Jacobian of this Riemann surface, which for all intents and purposes, you could think it just means I identified the Riemann surface with this matrix. And knowing this matrix, called the period matrix of the Riemann surface, is enough to recover, well, the Riemann surface itself up to conformal equivalence by, where was it written? I think it's on the previous page, maybe 2 pages back. Torelli's theorem, here it is. So a fact we noticed is that the dimension of the space of Riemann surfaces of genus G, G bigger than 2 for right now, is this, whereas the dimension of the space of matrices that look like period matrices of Riemann surfaces is this. And so there's a lot more period matrices, seemingly, than there are, or possible potential period matrices, as I call them. They're called Siegel matrices. Then there are Riemann surfaces. And so the question is to characterize, well, which such matrices with these two properties here are actually the period matrices of Riemann surfaces. Hybriding. So that's the sort of question we want to answer. And this is sort of a sketch of what we're going to talk about today, sort of.
I have a quick question.
Sure.
So what if the two matrices are similar to each other? Do they represent the same Riemann surface?
Right, yes. So I'm kind of skipping over some details for sake of time, but the appropriate statement is among all principally polarized abelian varieties, which are Jacobian. This terminology takes care of conformal equivalence of these things. So equivalence of the tori corresponding to this matrix. Someone's hammering around me? I'm not sure what that is. Can you hear that?
Yeah.
Okay, well, we're gonna have to deal with it, I guess. So equivalence of no, I can't focus. Equivalence of these tori is taken care of essentially by what you just said, up to essentially multiplication by.
You sure that's not your door?
No, my door is right there. So someone's hammering on the wall. Someone must be putting up a picture. It's a picture of me.
Certainly, of course.
All my neighbors love me.
Naturally.
So up to essentially similarity, this equivalence is defined. Does that answer your question, Fadong?
Okay, but does similarity will reduce the number of the?
It doesn't reduce the dimension. It just reduces kind of the space, what space looks like. It's a quotienting of space by, well, what is it called? Should remember from topology. Proper discontinuous action. So the group of similarities acts properly discontinuous on this space of Siegel matrices, and the quotient doesn't reduce the dimension; it just shrinks the space.
Okay.
Okay. So we talked a little bit about this Abel-Jacobi map and how to define functions on such Riemann surfaces in terms of this period matrix. And essentially, what we're going to come to today is, well, this same theta function from a different direction, which is going to be the direction of integrable systems. And the converse statement, which we're going to state in a second, I'm going to show it here, and then we'll actually talk about it, what it means. So the converse to this Riemann-Schottky problem, or sorry, not the converse, but the actual solution, It's going to be the following. One of these matrices is the period matrix of Riemann surface, if and only if it corresponds to, or its corresponding theta function defines a tau function for the KP hierarchy. So hopefully we'll define all of those words today in some form. And the theorem is due, it's pretty old, but it's still a good theorem. It's due to Krichever, well, at least partially it's due to Krichever. The idea kind of was motivated by Krichever. Novikov conjectured that actually the converse to Krichever's statement holds. And it was proven in 86 by Shiota. And I think this date is wrong. I didn't look it up though from last time, so sorry. Maybe someone will correct me while we're going or remember the date. So without further ado, we're going to start talking a little bit about integrable systems, starting with a little bit of motivation where they come from, ending with KP hierarchy and how Krichever actually constructed solutions. Sounds good to everyone? Is everyone okay so far with the background and the setup, more or less? Any questions? If not, then we'll continue. So integrable systems, and we have some experts in the audience today. So please correct me if you see anything. So a little bit of history. I think it was around the 50s, yeah, Fedon, that the kind of history of integrable systems starts.
Yes.
With Fermi postulates.
I would say 64.
64. Okay. So I'll tell the story in kind of a bit of a broken way, but it's still going to be sort of the same story. The story is going to start for us with KdV, which I'm going to write like this, and I'm pretty sure some of these numbers are going to be wrong, but in any case, they don't matter too terribly much. So this is called the Korteweg-de Vries equation. It was originally derived in the 1800s by Korteweg and his student de Vries, and it's meant to describe shallow water waves in a narrow channel. It's a dispersive equation. It's nonlinear because of this term. And so, well, in principle, it should be very hard to solve because it's a nonlinear equation of order bigger than 1. So in principle, probably should be a pretty hard equation to solve. It's an interesting enough equation in its own right, but as a fluid mechanics system, okay, cool. It's just another list of equation, or another equation in a long list of equations in fluid dynamics. So what makes this one so distinguished is compared to other fluid mechanics equations? Well, this distinguishing factor is this formulation of KdV as a compatibility condition of two linear operators. So this formulation is due to Lax, and I'm going to again skip over a bunch of details, but Peter Lax says that actually this equation, which I'll call KdV, is equivalent to the compatibility of two linear operators, which I'll explain in a second. Differential. And those operators are respectively L, which is minus dx squared plus u of x and t. So it's like a, hold on, unplug that. So it's like a Sturm-Liouville type operator, where the potential is actually the function that's appearing in KdV. And another operator A, which is and I think this is probably where Fedon will correct me. Some of my constants are probably off. Dx cubed plus 6 u dx plus 3 ux. Are they right, Fedon, or are they wrong? Or you don't know?
I don't know, but it doesn't matter.
Yeah, it doesn't matter so much. The difference will change whether or not this is plus or minus, I'm pretty sure. So these two linear operators in the corresponding linear system, L psi is equal to lambda psi, and dt psi is equal to a psi. It's a pair of linear equations. So notice that this equation is, the first equation is a linear equation. It's the Sturm-Liouville problem, the standard Sturm-Liouville problem. And the second is also a linear equation. It's dt of a function is equal to some differential polynomial in dx and psi. So it's also a linear equation. And the compatibility of these linear system, i.e. The condition that LT, let me write it like this, L dt minus a, this commutator is equal to 0, which is the same as writing DTL. I'm going to get this wrong immediately. I'm pretty sure it should be LA though.
I'm sorry, this A is not exactly linear, right?
It's a linear operator. So U is a given function defined by multiplication here. So it's linear.
Oh,
linear,
U is given. Okay, sorry.
U is given. So for given U satisfying KdV, this system is a linear system of equations, and actually they're compatible. So this compatibility condition between the two linear systems, which comes from differentiating this equation by T and well, multiplying this one by L, actually produces for you, well, tells you that well, this system is compatible. Essentially, you have commutatively partial derivatives if and only if the function U itself satisfies KdV. So this equation here is equivalent to KdV. And you can actually check if you want. It's a little bit of a tedious computation, but worth doing at least once in your life. That if you actually compute the compatibility condition of these linear operators, the one I wrote here, you'll find that well, you get KdV. So you get back exactly this equation. Again, I might be off by a sign. There might be a minus in here, but for all intents and purposes, it doesn't really matter. So the kind of magic of KdV is that this actually happens. You've solved, or it's possible to solve this nonlinear equation by going to, well, by linearizing it on a pair of differential operators. And the idea, which if everyone went to Fedon's analysis seminar, which I think most of us did, is that, well, you solve the first equation at time t equals 0, then you use the second equation to do the time evolution, and then you ask to recover the potential from the given spectral data. So that will give us a solution to KdV. So some more further comments about well, the KdV equations. So further remarks, all right. About what makes KdV so special? Well, we can think of KdV first as I'll write the words an isospectral deformation, or produces an isospectral deformation, deformation of the Sturm-Liouville operator. L. So for fixed t, this defines the Sturm-Liouville operator, and well, this condition here, and the fact that the eigenvalues themselves don't depend on time tells you that, well, when I change t, the spectrum of L is not changing. So we can think of, well, the KdV flow, the evolution of the function under KdV. Actually, well, what does it do? It deforms this operator L while preserving the spectrum. So we can think of KdV as having this nice property. Another fact about KdV is that it has an infinite number of conservation laws. A question?
Yeah, I have a question.
Sure.
So you say that if you know the spectrum of L, you're reconstructing U? Is that what you're trying to do?
You know, so that's sort of the inverse scattering direction. So I'll sketch that in a second. We're not going to talk too much about inverse scattering, but I'll sketch it. Actually, I'll sketch it right now, just for sake of clarity. So sort of an idea about how to solve this system of equations. So what Lax and a bunch of people at the time were very interested in doing. It's a whole industry. Dr. Ma can tell you all about it. So the idea of inverse scattering. So you want to solve the initial value problem. Well, ut plus 6 ux plus uxxx is equal to 0, subject to the initial condition that u of x and 0 is some given function u naught. So the idea here is first you solve the linear system. Well, I'm going to write L of 0. Psi of 0 is equal to lambda psi of 0. You solve this linear system for a given u, which is just solving a Sturm-Liouville problem. I say just solving a Sturm-Liouville problem, but there are several people in the audience that can tell you how hard this is in general. But maybe we could just solve the Sturm-Liouville problem. 2, you use the second equation. So use dt psi equals a psi to produce psi of t. So produce the eigenfunctions at a later time. This is sort of the easiest step. And you can think that you just, I'll write very formally again. Well, how do you solve this equation? Well, you just write e to the ta applied to psi of 0. And that's psi of t. So very formally, that's what you do. And finally,
So wait, 2 is saying that the eigenvalues don't change?
well, the eigenvalues don't change by hypothesis, essentially. the compatibility condition requires that the eigenvalues are preserved. So given that the eigenvalues are preserved, you get isospectral flow. It's if and only if, essentially. So if you assume the eigenvalues are preserved, then you get KdV and vice versa. So the first condition you solve. The second condition, you time evolve the psi t, the spectral data, if you will. And then the third part is to recover the potential, i.e. recover L of t, x of t, from the spectral data. So this is the inverse scattering part. And this is where people will mention words like Gelfand-Levitt and Marchenko transform, or Riemann-Hilbert problem, or the like. A lot of work is, there's again a whole industry in solving an equation like this in this fashion.
So steps 1 and 3 are the really non-trivial steps?
Yeah, 2 is also non-trivial, but it's in comparison easy. Again, we're not going to go along this direction just because, well, we're interested in something else. Just producing solutions is enough for us. And solutions of a particular type, which I'll explain in a second. So what was I talking about? We have that, well, KdV produces an isospectral flow of this Sturm-Liouville operator. It also has an infinite number of conservation laws. So infinite number of conservation laws. So for example, the total mass is conserved of the wave. Its momentum, its energy, so on and so forth, are all conserved quantities. A third property it has is that there are.
Sorry, Nathan, I know you're rushing to the glorious heights. Can you tell to kind of unenlightened what is actually total mass? What kind of norm of U it is?
Oh, sure. So it's just integral of U dx. So for our purposes, we're going to think that U is a function. We're going to talk about periodic KdV.
Oh, it's not absolute value or square, no?
We'll assume that the wave it's a positive wave. So it's yes, you would be correct. It's absolute value, but we're
okay. So it's L1 norm.
Yes.
And
so it's
and
the area
what is the next one? Momentum means
momentum,
the first moment.
Yeah. You can think it's like
XU.
Yep. And again, there's a whole system of conserved quantities. Like U squared is also conserved. So I don't want to get too much into it, but we'll see exactly why in a second. Essentially, these conserved quantities come from taking traces of L to the K. So each of these gives us a conserved quantity. And why are they conserved? Well, you could think that they're just sums of eigenvalues, and the eigenvalues don't change in time. And so, of course, they're conserved quantities. So these are the conserved integrals.
Nothing about conservation laws. Actually, Professor Cummins mentioned. First two is the integral of U, which is the mass, right? And also the energy should be U squared, the whole integral on the whole interval. And the angular moment is x time U, I think, something like that. But anyway, there are some links because depend on problem. The KdV like that, but any depending on problem, you may have different kind of formulations for the mass energy. And the most important things here is for the integrable system is we have infinitely many conservation laws, and we want to explore the further one. We know from Newton's theorem, right? We know the energy, mass, angular moment are conserved, but what are others? We have infinitely many. This is the most important, and physicists never answer about that, and we don't. It's really interesting to us, and we want to know, what is the fourth one and fifth one, or the total charge of the particles, or something.
Sure. So it's a super surprising property, isn't it?
Right.
There's so many conservation laws, and again, some of them become, physically, what even is it?
Yeah, what kind of?
But the fact that there are infinitely many is a very important property. I think the last important property I want to mention about KdV, what have I mentioned so far? Not that many things yet. Yeah, I've mentioned well, isospectral deformations. I've mentioned that they have infinitely many conservation laws, and finally, I want to mention that they have exact solutions. And this is sort of where we're going to rest in a second. So exact solutions. One class of them being the soliton solutions. So you can think that soliton solutions look sort of exactly like what I've drawn here. They're traveling wave solutions to the KdV equation. And I'm actually going to do a little short derivation of one because it kind of it will help us into the next piece of the conversation.
And they were first experimentally observed. I forgot the name of the guy who was rising
Right. So
on a horse. Yeah.
the original experiment were well, that one I don't know that far back, but at least numerical simulations were done in the 50s, where they found that these solitons are actually non-interacting in the sense that if I have two waves, so the two soliton solution and the second
I'm
wave.
pretty sure it was in 19th century that one of the English applied mathematicians was riding on a horse along the channel behind the solitary wave.
His name called Russell.
Russell?
Right. Okay.
All right.
Thanks.
That's very earlier. Russell is very earlier.
He did as an experiment.
So we're actually going to produce a solution to KdV in a seemingly well, non-standard way, but it will actually motivate sort of what we're doing later, or at least motivate a little bit what we were looking for, and what led Krichever to actually look for things like this.
Hi, Nathan. Russell has two high single reports for the London problem for Royal Society of London about the water waves. I think he has written down 2 reports, I think during 5 years, which is very beautiful. You can read about it. They're all about the water wave, particularly KdV, a lot of information about the KdV actually. Sure.
So what we're going to do right now is we're going to look for traveling wave solutions to KdV. So we're going to make a change of variables. Z is equal to x minus ct. So in other words, we're looking for solutions that look sort of like this one, where they traveled, well, on my screen, that one. So if we make the substitution, this change of variables, what we'll find is that well, c times u prime plus 6 u prime plus u triple prime is equal to 0. In this equation, we can, well, I'll say clearly integrate, and we're going to. This gives us c u plus 3 u squared plus u double prime is equal to constant number 1. And well, if I multiply everything by u prime, I can integrate one more time. So if I multiply by u prime, this becomes c over 2 u squared. This becomes u prime, or sorry, u cubed times, not just u cubed. This becomes, well, u prime, oops, u prime squared with a 1/2, and this becomes just kappa 1 u. And if I rearrange, so rearranging, oops, what do we find? Well, by rearranging, I find that u prime squared is equal to u cubed, or I'll write it like this. It's just a third order polynomial.
You should add another constant term, I think.
Yeah, thanks. Good catch. So if I integrate again, I should, of course, add an integration constant. So the important point here is that, well, the form of the equation. It's first derivative squared is equal to third order polynomial in u. Does anyone recognize the form of the equation? A few should. Any takers?
Weierstrass function.
If I don't give it away, but yeah. So it's the Weierstrass function, up to a constant, so shifted by a little bit. So this is exactly the Weierstrass equation. I don't know if it's called the Weierstrass equation, but I'm going to call it the Weierstrass equation. Whose solution is the elliptic function p of the variable z. So a constant times this plus another constant, different constants, will make this function satisfy exactly KdV. And actually, if we take an appropriate limit, we'll actually end up with a one soliton solution to KdV. You just take a limit as one of the periods goes to infinity. But we're not going to go too far into that. The important point I want to emphasize here is that actually we have well, a solution which is an elliptic function. It's algebrogeometric. So it's a function which lives on a Riemann surface, or at least the spectral parameter itself lives on the Riemann surface. So these are the sorts of solutions we're going to want to look for, algebra geometric solutions. And it's sort of the first hint of a connection between KDV and or equations like KDV.
I'm sorry, but when you say on Riemann surface, in this particular case, you mean simply torus?
Yeah, in this case. And I conjecture that it will happen. The phenomena is much more general, that we can find solutions that look like this, which is sort of the direction we're going to be going in a second. But we'll need to tell a piece of a story that will take a few minutes. So the idea is that, well, what we're going to look for eventually are going to be solutions where the spectral parameter itself lives on a Riemann surface. So I'll explain exactly what I mean by that in a second. And to do this, we'll need to go to, well, the KP hierarchy. So we kind of mentioned here a couple nice properties of these equations. They can be considered as isospectral deformations of a particular differential operator. In this case, it's L. They have infinitely many conservation laws, and they admit exact solutions. For our purposes, at least right now, that's what we're going to take as a definition of an integrable system. And we're going to pose the question in order to, we'll come to what Krichever found. So question. What is the most general I'll say structure. That might be a better word. Structure with these properties.
This is a terrible question.
I agree, but to avoid talking about the fine details of well, what's meant by integrability here, that's going to be our question.
No, the question is property.
In the best traditions of Marxism-Leninism question.
Maybe so. What was your comment for that?
What?
What kind of property you mean?
So the above properties, that there are exact solutions, an infinite number of conservation laws, and they act as isospectral deformations of some differential operator. So those are the kind of properties we want.
Yeah, I mean, from DE point of view, you know, I mean, this is, I mean, you just derived very special kind of solitary wave solution, very, very special. This is just a single solitary wave, right?
No, I agree. So I only derived the one solid solution.
You know, so
I mentioned that there are more, but I didn't say or prove anything.
So from DE point of view, this is actually just Frobenius decomposition. So Frobenius decomposition, I mean, you link the higher order dimension or higher order PDE to the lower order PDE and further to the classical ODE, in which we can integrate, of course.
So we're going to talk about, sorry to interrupt, we're going to talk about the KP hierarchy now.
Sorry,
Yeah.
I'm sorry.
Sure.
There's, you know, there is no 5-year plan, so we're not rushing. So let me just repeat what you said. So you start with KDV, you look for the whatever stationary wave, right?
Solitary wave.
Solitary, whatever it's called. Yeah. You do the change of variables, you solve it explicitly, and you get, in terms of variable z, you get
traveling wave solution, yeah.
Right, Weierstrass function, which is doubly periodic
Just
function with 2 poles.
Yep.
So these poles, if you go back to physical situation, these poles of Weierstrass functions, what do they represent actually?
Well, it depends whether or not this is supposed to be a solution representing something physical or not. If the poles lie on the real axis, then clearly it's not going to represent anything. It's just a wave that blows up.
Mm-hmm.
Now, if you take, again, like I was mentioning, what I didn't say, you take limit as this period goes to infinity in an appropriate way. You take limit as I tau goes to infinity. What you find is that you end up with the usual solitary wave solution that Dr. Ma was mentioning. I'm going to write A plus B hyperbolic secant squared.
Mm-hmm.
So this is the sort of solution you end up with. If you take that kind of limits, you end up with the one soliton solutions. And in fact, what we're going to find is that, well, this sort of computation can be generalized sort of significantly. But we need to talk about the KP hierarchy to do this. And you can think that the KP hierarchy, so maybe a good description for people that like algebra, it's like a universal enveloping hierarchy. containing all other hierarchies and all other nice enough integrable systems like KDV. So that's sort of well, what it is and why to look at it. Well, again, it acts like a universal enveloping object for the category of integrable systems, if you want to say those words. And it's also sort of the reason that KP hierarchy appears in a lot of places and not some other hierarchy. It is the sort of biggest hierarchy that, well, by quotienting, by sub-hierarchies, you get any other hierarchy you want. But what is the KP hierarchy, I guess? I haven't said that yet. So that's sort of going to be what we talk about for a while now. So what is the KP hierarchy? We're going to define seemingly something very formal to start with. And as we go along, we'll get less and less and less formal until we actually end up with something concrete that we can construct explicit solutions to. So the first thing we need to define is the ring of pseudo-differential operators. So I'm going to say the word pseudo-differential operator. I'll explain what I mean shortly. So
listen, I want to mention one point here.
Sure.
We are solving PDE right now, which are nonlinear anyway. Let's look at the inverse scaling transform, right? Lux pair scheme. So in the Lux pair, the KDV equation just corresponds to the isenspectral case, right? But you still have non-isenspectral case. So now, let's say lambda t equal to lambda. So you get another flow. That flow is actually the symmetry. We call it additional symmetry to the KDV. So the symmetry still transforms solution to solution. So once you determine that symmetry, you get another kind of solution.
No, sure. Well, we're going to talk about that shortly. So I'll mention that for KP hierarchy.
So many.
I'll mention it for the KP hierarchy. So you'll see it coming. So you're ahead of the game. So the ring of pseudo-differential operators, I'm going to denote by psi, and I'll explain what they are right now. So I define, I consider the ring of formal Laurent series in the variable x and t. So formal power series, sorry. And I consider the collection of first differential operators, D. So these are a set of linear differential operators. In X with C of xt coefficients. So an example of such an operator is something like I wrote before for KDV. Either of these two operators, L and A, fall into that category. Both are, well, linear differential operators, and both have coefficients living in this ring. I mean, it depends on what U is, I guess, and so it depends on the kind of solution we're looking for. But for right now, to treat things a little bit more algebraically, we're going to take them to be in the space of formal power series. So this is the collection of differential operators. It's going to be a subring, an important subring at that, of the ring of differential operators, or pseudo-differential operators. So what is a pseudo-differential operator? Well, it's the algebra of, well, I need to define a symbol first. Maybe that'll be best. So I define this symbol D inverse. So what is this D inverse? How does it act? Well, D inverse applied to D. D here is d dx. It's the same as D inverse is the identity operator. And we can think that D inverse is just like integration and setting the integration constant equal to 0. So for all intents and purposes, that's exactly what D inverse is. I'll write that in words. D inverse represents integration and setting the integration constant equal to 0. So the ring of pseudo-differential operators now, I'll write like this. It has C of x inverse coefficients, and it is well, a ring itself over D and D inverse. And it should be, sorry, let me write it like this. It should be polynomial in D and Laurent series in D inverse. So it should be round parentheses here. let me write it like this. Probably the best way to write it is this. So this means Laurent series in D/D. And I'll explain exactly what I mean. So what does a generic element of this look like? We'll instantly clarify any questions. A generic element of this space looks like the following. So it looks like this. It's going to be sum j equals minus infinity to n. And n is called the order of this object P. I'll write aj of x and t, and then d to the minus, or d to the j, I guess is how I wrote it here. And these objects come from the formal power series. So in case you're not familiar with the notation, the round brackets mean Laurent series. The square brackets, double square brackets mean power series. And a generic element of this ring looks like this. So this is in psi. Let me put a box around this. So is everyone okay kind of with how the generic objects in here look? How they act? I can explain that in a second. Does it look okay? It's a little scary looking at first, but well, you get used to it. So any questions about at least the definition? Yes, no, I'll take that as a no.
Nope.
Okay, good. But on follows. So of course there's a natural grading to this space, and I call psi m the set of pseudo-differential operators, p and psi, whose order is less than m. And in particular, I distinguish psi minus 1. I call it psi minus. So now I'm following the notation from Shiota's paper, just to kind of try to keep in line with what we're going for. And it's well, it's not even a theorem, it's just an observation. That psi decomposes as, well, the space of differential operators. So remember, D is the space of ordinary differential operators, linear differential operators with these kinds of coefficients, only in the variable x. Direct sum with psi minus. So we have this nice direct sum decomposition. So we're now actually pretty close to defining the KP hierarchy, and it's going to kind of very closely mimic, well, the first property here, that it should have some sort of isospectral property. So that's sort of what we're going to ask for. And given that, we'll be able to construct a whole hierarchy or a collection of equations, which, well, are mutually compatible, all have infinitely many conserved quantities, and can be solved via the method of inverse scattering that was mentioned before, as well as admit solids and solutions, blah, blah, blah. So any questions about the definition I just gave, about the form or the decomposition of this space? I want to make the details clear so we can be clear later what we're talking about. So any questions about that? If not, then I'm going to go to the next page very slowly. Okay. So clearly from that decomposition, an element P, in psi can be decomposed into two parts. P is P plus P minus, where P plus is a purely differential operator. So this lives in D. And P minus is a purely pseudo-differential operator. This lives in psi minus. So it only has coefficients in this D and X function. So of course, if I have a particular operator P, I can consider its projection into the space of, purely differential operators. So what is the KP hierarchy? I'm going to say in words. The KP hierarchy is built as follows, or constructed as follows. So it's a sort of constructive definition. I consider an element L, which belongs to, well, the space D plus psi inverse. So this means generically what an element of the space looks like. It is well, the operator derivative plus something that's purely pseudo-differential. So it doesn't live in, it is not differential operator, it's not even a constant. It acts as D inverse. So we take an operator from here, and we want to consider isospectral deformations. Of this operator, all isospectral deformations of this operator. So we consider it depending on a parameter t, or possibly an infinite collection of parameters, t1, t2, so on and so forth. For our purposes right now, we're just going to take it to depend on 1, because that's all I wrote at the beginning. And what do I mean by isospectral deformation? Well, I mean it preserves the spectrum. So a theorem, so L is L of t, and a theorem is that if I define the following operators, bn's, which are L to the n. So I take L, I take n powers of it, and then I project into the plus subspace, the purely differential subspace. And I consider the equations dtn L. So I differentiate with respect to the nth parameter. Here it's just the first. You can think that we just call the nth parameter the first. It's just whatever flow we happen to be looking at in particular. Commutator of bn and L defines an isospectral flow. And actually it follows from, furthermore, I'll say this. This system, or the system of equations, are equivalent to the following. This is actually where I have to start introducing more parameters. So you can think that for each of these bn's, each n I pick, I introduce a new flow direction, so another isospectral flow. So I have, well, that L depends on, well, for right now you can think just two parameters, t1 and t2, or tn, tm, whatever you want to call them. The point is that we only consider two at a time. So there's a lot of parameters, but we only consider pairs of them individually. So it's not too terribly complicated. And it's equivalent to the following system of equations: dtn bm minus dtm bn, and it's either plus or minus. If wrong, will correct me. I think it should be bn bm, if I did things correctly, is equal to 0.
bmn.
Let me see. Yes. Okay, you're right.
Curvature equation, right?
Yeah. Which is the same as writing this pair of zero curvature conditions. So it's an infinite set of commuting vector fields. Where it defines an infinite set of commuting vector fields. And furthermore, it's equivalent to the following. Well, the system actually gets linearized. So that is equivalent to the following system of linear equations. L psi, and I'll explain what psi is in a second, is equal to k psi. And so all right, actually, the following is also true. L psi is equal to k psi, and dtn psi is equal to bn psi, which is n equals 1, 2, so on and so forth. So essentially what we've defined is an infinite set of equations, which all, first of all, are mutually compatible. That's what this condition says, or this reads. All are isospectral because of this condition. And we'll all have infinitely many conservation laws, essentially from, you can think this condition. Why? Well, because if I take trace of a commutator, I always get 0. And so traces of these are preserved with respect to the nth flow. So all of the nice properties we had before are seemingly present in this very large object I've defined. And what do I want to say? Well, except for one property that we've kind of neglected, which is this exact solutions thing which we'll deal with in just 1 second. So let's take a moment to pause and try to wrap our heads around what the KP hierarchy is, I guess, because it's a very large object. You have a question?
Yeah. May not be a question, but anyway, I mean, remark a little bit. Yeah, if you're starting with, this is KP, you are telling is correct, no problem. Starting with this kind of a pseudo-differential operator L, right? You can start with a high order. The high order under similar transformation could be reduced to the first order. I mean, so no problem. With the first order, you can classify all of them with a different kind of potentiation. I mean,
right. So this was the comment I mentioned at the beginning.
In front of partial. So this is a Halidim hierarchy. What I want to say is you can classify all kind of finite order pseudo operation which can generate the commuting flow, and 3 hierarchy. The standard one is KB, and the second one is modified KD, and the third one is Halidim hierarchy. So we have only 3. We cannot have other more. And this kind of hierarchy can be presented by using, I mean, the tau function and also actually.
Yeah, so I'm getting to that. So
actually, geometrical way, like sort of, right. 3, yeah, no more. If you really want to classify, you can, yeah, under the similarity simulation and the similarity transformation. Yeah, the key is most of the standard one. Yeah. That's very important. Yeah, if you really you cannot just generate more, but you can have many reduction from KP. Yeah.
No, sure. So that's my comment at the beginning. That KP acts as a universal enveloping hierarchy for all other hierarchies. It's like a universal enveloping object for this category of things.
Right. You can have a reduction, but anyway, I mean,
sure. So the Gelfand decay.
Without the reduction, you have 3 hierarchies. You can classify.
Sure. So there are the Gelfand decay reductions, which you take quotient by. You require that the second term in this expansion.
Have you considered about the modified KP hierarchy? Yeah.
Sure. It's contained within this one.
No. It's not contained here. It's not contained here.
It is. I'll show you how.
Construct. You just get a KP. So modified KP is not there. Modified KP.
It is, and I'll show you why or where. So if I take the second power, and I require that the second power of this operator is a purely differential operator, so lives in D, and then I make the Mura transformation. Then I end up with the.
half power.
I mean, under the standard way. So if you modify, of course, the potential you combine together. So I mean, the dependent variable doesn't change. Under the original setting of the dependent variable, you have 3 classes. I think what I mentioned is one is the KP, one is the modified KP, as a Halidim hierarchy in this kind of setting up. You cannot make them, I mean, equivalent to each other. No way. No, there are no, I mean, equivalence between them. But you can have many modified equations. I mean, how to say?
No, okay. So we'll talk about that later. So we'll talk about that.
You have to
I want to get to the theorem of Krichever.
No, you are using transformation. For example, transforming U into the U derivative of U plus U squared. That's another story.
So it produces the KP equation. So a comment here just to kind of become familiar with this hierarchy. If I take n is equal to 2 and m is equal to 3, in this pair of equations here, so that means I take L cubed, L squared, I take their positive parts, I take their commutators. This equation here reduces to the KP equation, which you can think as a 2-dimensional analog of KdV hierarchy. Something I was mentioning before when I was talking to Dr. Ma, if I require additionally that L squared is actually a purely differential operator, then, well, that same equation that I've written down before actually reduces to the KdV equation, so the original KdV equation we had. And there are all sorts of reductions we can make, which produce other integrable systems. Depending on what you want to do, you can produce other things. What we're interested in is looking for algebra geometric solutions. So what properties does this operator psi have? Or this function psi have? So psi, so the next question to address is what is psi? It's going to be called a Baker-Acciaser function, or a Baker function, or an Acciaser function, whatever you want to call it. And for right now, it's a formal object. And what Krichever essentially did is made it not a formal object. He made it an actual well-defined thing on which these equations actually can be, well, realized, linearized, and, well, rigorously defined. So it's called the Baker-Acciaser function. What properties does it have? Well, Psi is an object that looks like the following. It's a formal sum with coefficients again coming from, well, that ring that I written before. So AJ's are formal power series in X and T. And maybe I should make a notation here. So J equals minus mu to infinity. K to the minus J, e to the kx plus a polynomial in k, t, and then possibly plus more. So for each tk I have, I multiply it by polynomial. And how do you determine what this polynomial is? So what is this polynomial? Well, the polynomial is determined by requiring that if I apply the operator bn to psi, this is the same thing as dt psi.
So here T is a vector.
What is? For a second, yeah, you can think this is a vector of polynomials, and this is a, for you at least, you can think this is vector of polynomials, and this is vector of times. But for our purposes, there's just one time and one polynomial, just to make things look better.
Product of P and T, right? Basically.
Yeah, so you can think it's inner product.
Okay.
But for our purposes, it's just one time and one polynomial. The whole hierarchy will be built in exactly the same way.
No, this, I mean, for KP, you need the two.
Yeah, you need X and Y. So there are two. Yeah, you're right. For KP equation, but we can think we're dealing with KdV for a second. But the story is going to be the same.
Yeah, yeah.
So the magic comes in actually justifying that there is such a function. So do such functions exist which satisfy this type of equation, and for which the linear system or the system of equations is actually linearized on this Baker function? And the answer is yes, and it comes by requiring that the function itself lives on a Riemann surface. So psi exists, and I'm going to write lives on a Riemann surface, meaning that this variable k that I've written is actually well, a local parameter on some particular Riemann surface. So I'll write down the technical lemma due to Krichever that essentially allows us to do all computations afterwards. Maybe a word before I talk about that on why this function psi is so important. Well, first of all, it is the system, or it is the function on which this system of equations is actually linearized. So it is the function on which the system is actually linearized. And second, we can actually produce solutions just knowing what psi is. How? Well, you make, what is the name of the shift? Do you remember? It's like I forget the name now. It's someone's name, Sato shift, I think. So, say again? Sato shift, yeah?
Yes.
So I make the shift of each of the variables.
Right.
Third or squared, this is B, I'm sorry. Let me write again.
Then the flow is coming out.
So 2 k t2 minus 1 over k squared. So essentially, this function that I'm writing now is called the tau function. And don't worry too much about what a tau function is. You could think that the tau function essentially just means solution to the hierarchy. So if I can construct such a function psi explicitly, what does it bind me? Well, it binds me to this thing called a tau function by making this change of variables. And the tau function you could think is actually just a solution to the hierarchy. How is it related to a solution? Well, a solution is produced
Bilinear form.
by differentiating
D log.
Yeah, log of the tau function. So solutions are produced to the hierarchy in this way. So essentially, all we need to do now is construct explicitly this function psi. And where is it constructed explicitly? Well, this is Krichever's bright idea, was to actually realize this on a Riemann surface, because the equations themselves actually become well-defined equations, and they're uniquely defined because of the condition that this is supposed to be, well, this function psi is supposed to be a well-defined object on this Riemann surface. So the theorem says the following of Krichever, and then I think that's it for today. Given the following data, we can produce a unique I'll call it Baker archies function, or is given by psi function. So the following data is one, a Riemann surface with marked point. Two, well, I'll say words and then I'll explain what they mean. D is a positive divisor of degree, the genus of the Riemann surface. And it's positive, I should add the words non-special here. So what do all these words mean? I pick G points on the Riemann surface in a non-special position, meaning they're not branch points, essentially. And I pick G of them. G is the genus of the Riemann surface. And given these two pieces of information, well, psi will have the following property. So there is local parameter K, which equals the point P infinity. So let me write like this: K inverse is 0. So 1 over K, you could think it's like it's the parameter 1 over K at this point. So there's local parameter near P infinity such that well, the function psi has exactly this expansion. For any given polynomials P, and in particular the ones coming from the KP hierarchy. So well, one can produce explicitly now. Well, given that this lemma is true, and it really isn't all that hard to prove either, it's just a simple application of Riemann-Roch theorem and a little bit of manipulation with data functions. So you can actually produce, well, function on Riemann surface with these properties. So what properties does this function have? It has poles at the positions or the points that you picked from this divisor. It has an essential singularity at, well, this special marked point, which you can think of as the analog of infinity. And well, it has the nice property that the equations of the KP hierarchy are actually linearized on it. And from that, we can actually produce, well, a solution to KP hierarchy. So I think the last thing I want to say is the actual conjecture of Krichever. So or conjecture of Novikov. So the magic of this construction is that it can actually be done explicitly. Not only can I write down the psi function and claim that it exists in a Riemann surface, but I can actually express explicitly in terms of theta functions what this function psi looks like, and also what the corresponding tau function tau looks like. In terms of these, where did we talk about theta functions a couple of days ago? Yeah, explicitly in terms of theta functions. And of course, this theta function on the Riemann surface will be defined in terms of, well, the period matrix. So, well, Novikov had a very bold conjecture. So Novikov is Krichever's advisor, and he had a very bold conjecture that actually, well, this is a characterizing property of Riemann surfaces. So such, because I can similarly, you can kind of, something that Novikov noticed that you can actually do the same kind of construction. You could ignore that we did anything with the Riemann surface and just start with, well, the theta functions and try to write something down. And you find that unless, well, which by trial and error will say, unless that period matrix corresponds to the period matrix of a Riemann surface, you don't get a solution to the KP hierarchy. So the conjecture of Novikov is that such a construction necessarily requires that the theta function is Jacobian, I'll say, which just means that it comes from Riemann surface and not just a generic abelian variety. So Novikov conjectured this fairly boldly, although it was kind of, he was a very, he had motivations, of course. But it's a very bold conjecture if you don't know anything about either subject, like me. And it actually ended up being true. The motivation actually sort of comes from this thing called Birchnell-Chondy theory, which I wanted to discuss, but we kind of ran out of time today. About commuting operators, commuting differential operators in one variable. So it was well known that commuting differential operators in one variable will necessarily define a spectral curve that they live on. And this essentially is the generalization of that idea, that deformations of that spectral curve actually correspond to, well, flows in the KP hierarchy. So the conjecture is actually not only a conjecture, it's a theorem due to Shiota in '86. that the conjecture is actually true. And it relies on essentially the techniques from Birch-Nell-Chondy theory and also Krichever's construction. So actually half of the conjecture is done by Krichever. The other direction that if I have, well, theta function, solving KP hierarchy, I can, well, reconstruct a corresponding Riemann surface and the set of data that I laid out before, which I'll call the spectral data in some sense. So actually the two end up being equivalent. And this is actually what I was saying before is a solution to the Riemann-Schottky problem. That, well, this set of data is equivalent to a solution to the KP hierarchy. So I don't know, I can discuss that more if you guys want to hear. I'm kind of out of time today, so I'm going to stop talking, but any questions?
Well, at the end, it's certainly not at all the solution that neither Riemann or Schottky had in mind.
Sure, I agree.
Because the problem is, given a symmetric matrix, is it a matrix of periods for the Riemann surface, or is just a symmetric matrix? And
yeah, and well, what I think this says that the answer can be very complicated, and in fact it is.
Yeah, well, that's good, but I still think that something can be said in a very simple partial case. Like if you have one positive number that you know that number is always a modulus of an annulus. So now suppose you have what would be 2 by 2 matrix, symmetric matrix. How can you say that this is a matrix of periods for triply connected domain?
Well, the statement here is that you write down the corresponding tau function, which is doable. You check if it solves KP hierarchy or solves a particular equation, say just the KP equation. And if it does, then you're good to go. It's period matrix surface. If it doesn't, then it doesn't. But
right, but I think in 2 by 2 matrices, there is still hope to get the equation.
So it depends then on what kind of solution you're looking for.
Well, I'm looking for a variety, for an equation which defines variety of period matrices in the whole set space of matrices.
Sure, and this sometimes does. It defines via KP.
Yeah, but it doesn't tell you whether it's. It still doesn't tell you whether it's.
It does.
I don't think so.
Sort of indirect.
Whether it's a triply connected domain or it's a sphere with 2 handles. I don't think so.
This does. It does for sure. It's just, again, how practical it is and actually checking is a different story. But in principle, it does. So I don't know. I can talk more about this next week. I was hoping not to talk about this anymore, but I mean.
Well, if you can like take one example, as I said, 2 by 2 matrix, and tell me exactly what is the condition on the entries that makes it a period matrix.
So again, it's not so explicit, I think, is what you want. You want something very, very, very explicit, which is not.
Well, it could be implicit. It just.
So the toy is this: you take matrix, you take theta function, and you take the corresponding period matrix, and you write down what should be a theta function solving this case. You write down this tau function. So you write down explicitly this tau function, which is an expression in terms of theta functions, explicit expression. Then you write down the KP equation. You plug it in. And if it solves, well, it solves. If it doesn't, it doesn't. There's another nice check that you might like better. It's called phase Trisecan identity. It's actually equivalent to an identity satisfied by tau functions of KP. And it's purely, I mean, it doesn't mention anything about integrable systems, although it is sort of an integrable systems thing. It's called phase Trisecan identity. Maybe that's something you would like.
Let me, no, I mean, I understand what you're saying, but it's still not what I'm asking. Let me put it the other way. You take a triply connected domain in a canonical form. Either it's a circular domain, so all 3 boundary components are circles, or it's a plane with three vertical slits. And you take triple connected domain, and you can more or less explicitly, in terms of period matrix, and I did it in my course, write down the conformal map, let's say on a Hilbert map on the plane with slits. But there is a bigger problem, and you can't explicitly write down the coordinates of those slits and the length of those slits.
Yeah, so the same problem arises
That
here.
would be solution of Torelli's, that would be Torelli's theorem in this case. And I still think that when the topology is fairly simple, I think it's possible. It probably will involve inversion of elliptic function, but I think the solution is possible. But that would be really a nice problem to solve.
Sure. So I'll say this maybe. Unless anyone else have questions before Dr. Ma?
I think, of course, I think Professor Cummings raised some very general question about the Riemann surface or classification of Riemann surface or the classification of theta function. So in solution theory, we have two aspects actually. This is one of the problem actually, very important. This is just, in the pure complex, variable field, right? Complex function field or some kind of limit field. And in solution theory part, we want to classify the equation. So normally we are given a PDE and we want to link the PDE with some kind of theta function or some kind of Riemann surface, which help us to present a geometric algebra solution to the PDE. And this is one of the, but what kind of Lux pair and what kind of Riemann surface we can choose, because so many Riemann surfaces, right? We can have Suli infinity and point or whatever. Yeah, different kind of Riemann surface. Yeah, and we want to classify them. What kind of Riemann surface we can use to present the given PDE solution. And the other hand, actually, this is one of the problem. Other point, if you're given Riemann surface, what kind of PDE could be associated with this kind of PDE, with kind of given Riemann surface, which has the theta function as algebra solution, or we can present their solution by using the theta function defined on that kind of Riemann surface. This is very hard problem, I think. Yeah, so classify Riemann surface which can associate with integrable system. We have infinite many conservation law, infinite many flaws, community flaws. This is one. The other part is given the PDE, what kind of Riemann surface we can find, which we can use it to present geometric algebra. Because this is correspondence. I think it's not very clear. I think in the convolutional case, for example, we are now studying the water wave. In the water wave, different kind of solution phenomena we have. For example, we have Flicken solution. The Flicken solution, we don't know what kind of Riemann surface you can use, because the Riemann surface could be very geometric kind of algebra code we should use.
I think to answer that,
probably fifth order or sixth order, we can use to present the geometric solution, and then we don't know how to classify this kind of curve clearly.
The answer is with anti-holomorphic involution. If you have that, you can produce real solutions to PDE or KP hierarchy or whatever integral system.
KP is a very standard way. Really, KP. If you look from a mathematical point of KP, look at pseudo-differential polynomial. The potential is just one by one arranged there in front of all of the differential operator D. So very clearly. But if you sum of is down, if you sum of 0 in your L, the coefficient, some coefficient in the L is 0. Then this is the reduced case. Then what kind of Riemann surface you can have? You should use to present their solution, algebraic geometric solution, by using theta function. So that's really, I think this is a really question for solution people. actually.
So one more comment about to answer sort of Dima's question about well, just a nice connection between
There's a KB case really just
in
beautiful.
algebraic geometry. So
Yeah,
there are
KB
other solutions.
is just
Other-
systematic,
other problems.
beautiful. Yeah.
And there are other types of problems arise in algebraic geometry, which are solved by integrable systems. Another being this very beautiful solution due to conserved of intersection numbers on the moduli space. They can actually be computed by.
Yeah, for sure. If you're more general, you have to use modular space, of course, because you really just cannot, establish the analysis on that or geometry on the curve.
You can. That's the point. So the intersection numbers can be computed via derivatives of tau functions.
Right. What I can suggest one question. You can think about it. You take the because you are L, right? Your L is partial plus partial inverse, and you negative one. I think you partial you plus you negative one partial inverse, and
right.
You negative two partial inverse two. You let you negative one and you negative two equal 0. Can you get the Riemann surface?
Sure, it's just a reduction.
I don't think so, because you can try it, but anyway, I don't think so. Yeah, and you can try this example. Yeah, you can try. Let some coefficient in L is 0 or 2 0. 1 is 0 actually is KP. The 2 0 is actually 2 0 probably had it in complete. You take some of 0. You take this. Yeah, you take the partial negative 2, right? The partial negative 2, the pseudo operator. The coefficient in from that 0. Then tau function doesn't exist. So it's hard. You really to pick the Riemann surface, which is really hard, I should say.
And I think Dima has the same question. So how explicitly can you?
Yeah, okay, I'm sorry.
The answer is not there. But the point is that they exist and they're possible to write down.
Try some example. Yeah, definitely you will explore more. And
so again, it's possible to write them down, just not as explicitly as you'd like, but it's still possible. Okay, so I think that's it.
Want
to speak next week? Anyone on?
How? Yeah, problem is how to pick. Yeah.
Brittany, you want to speak? Let me stop recording real quick.
Let me think about it.